Yes, students, I'm a little bit in doubt about what to do. In the study guide, we see chapter 14.6, and that I also want to do, but only the thing is, what will I do? What kind of things I will do? Let's repeat something, and most people will know it already from linear algebra, or they have already done it several times. The determinant of a 2 by 2 determinant, you have a times d minus b times c. And I have told you, if you look to it as two vectors staying near each other, then that determinant is in certain sense calculating the area of the two vectors with span and parallelogram. So if you have your x and here your y and 0, then you have here, in certain sense, the area is determined. But be careful, you get some number here, and determinant gives you always a number, and it can be positive, it can be negative. Because if you change those two vectors, you change them and you calculate again at the same way the determinant, so this one times that one minus the other one, then you get the opposite value of it. So be careful. And what did we do? Now we calculated with that such a kind of a determinant. We calculate the correction term of transformation. For instance, here you have the from the xy coordinates to the polar coordinates. Now, that's not completely true. In certain sense, I do the other way around. If you have polar coordinates, then I'm calculating the xy coordinates. Then you can calculate that direction term, correction term. You have your dA in the integral, that is dx dy, and if you do it in the polar coordinates, you get r dr d phi. And what are you then doing? First of all, you calculate the Jacobian matrix, and let we here let it depend on the radius and the phi. And the Jacobian matrix is nothing else than the xdr. And then I have to search to see, because I don't know exactly the the order of the way they um, now let's then do the x coordinate is the first coordinate, that we then do the x d phi. So the first coordinate, the x, we differentiate to the first variable of the polar coordinate, in this case the r, and then we differentiate the first coordinate to the second variable phi, and then we have here the y, the r, the y, the phi. This is the what is the Jacobian? The Jacobian is the determinant of this matrix. And you have the matrix, and then you can calculate the determinant. And if you do that, you get out, in this case, you get out of it dr d phi, if you do it because. But if we now should have changed the x and the y of names or something like that, then we should not have gotten we should get something else out of it, and that we will have got you will get minus r out of it. And so if you see those integrals in Adams, you see always the absolute value of the Jacobian. So then you have the absolute value. So the Jacobian is the determinant, and then with the correction term you take the absolute value of the Jacobian. So absolute value of the value out of determinant. So be careful. So don't see those vertical lines as the lines of the determinant. That is not the case. Now, what to do in general, and then, in general, you know, um, let's go to spherical coordinates. And be careful with those spherical coordinates. As I told you already, we always have a right-oriented vector space, so x to the front of you, y to the right, and the z goes up. And now I think the z-axis I can better take something longer than what is staying here, something bigger. So I will have this one here. Now, what to do now for the spherical coordinates? You have the Cartesian coordinates, x, y, z, and then the spherical coordinates. What do we have? You have a radius, a phi, and a theta. You have two angles. And what is the case? Now, if you have some point in the space, and then I hope that the sketch will become well. Here you have the point x, y, z. You have the origin. You have some line from the origin going to that point. Now, and then you have the following. You have you look to the x-axis, and if you go in the xy plane, you have the radius and the phi. And so you have here, not the radius and the phi, sorry, I keep my words back. You have an angle phi in the xy plane, and here from the positive part of the z-axis you have the angle theta, and that's important to now if you have those two angles, you can describe your x and y and z. Your x becomes just like the polar coordinates r times the cosine of phi, y is r times the sine of phi, no problem. And now you get your z variable, and that z variable, now you see the angle is measured from the positive part of the z-axis. So if you fill in theta is 0, you are at the z-axis, and so you have here the cosine of theta. Now, and if you have here the cosine of theta, then the other two has to multiply by the sine of theta. Now, and I hope that you see, if you fill in everything, you have always to get the following, that you have x squared plus y squared plus z squared, that has to be equal to r squared. And then what can you do with your radius is always greater or equal to 0, or I can also say greater than 0, then the Jacobian will never be 0 if the radius is 0. But okay, let's do radius greater or equal to 0. The phi, yeah, you can take what you want in certain sense, but if you have some interval of length to pi, I often do from minus pi to pi, but you may also do it from 0 to 2 pi. That in certain sense it doesn't matter me if the length of the interval is 2 pi, and the theta, that is of importance. Theta you have to take between 0 and pi, and that is just one, and that is just an interval of a length pi. So this interval length 2 pi, and here your interval length pi. Yeah, you can also do other things quite well, but let me do this, and maybe if you are very a real mathematician, you will have that no points are falling together, so you take phi greater than minus pi and less or equal to pi, so you have a length pi, the 2 pi. And therefore sometimes you can also let the r may be better greater than 0. Okay. Okay. An other way could be, but I say could be, and that you have, for instance, you only take your phi greater or equal to 0 and less than pi, but then if you want to have all things on the sphere, you have to let your theta going. You have to let go from 0 to 2 pi. But that is yeah. Let we speak together that if we are not doing something else, that we will use this most of the time. And if you look to that figure, yeah, what do you have? Then you have, in certain sense, you have the following, that you have the R3 positive oriented, and then in certain sense you have, if you theta's between 0 and pi, 0 and pi, if that is your angle theta, you have a half of a circle, and that half of a circle you rotate around the z-axis, and if you rotate it around the z-axis, you get your sphere. So this half of a circle is rotated around the z-axis and you get your sphere. And the other one, How can you look to that? That you can look as follows, that you have your xy plane of xyz space, Euclidean space, and if your phi is between 0 and pi, you have in certain sense a circle in the xy plane, half a circle, and then with your theta going from 0 to 2 pi, you rotate that half a circle around the x-axis. Yes, you rotate around the x-axis, and so you get your plane. Your plane, your sphere, I mean. And so you can also look to it. But let we always do that one, the orange one, let we most of the time do that. Now, to um, to calculate the correction term, you have first to calculate the Jacobian, and in this case then it will depend on the r, the phi and the theta, and the Jacobian, that will be the determinant. Be careful, and then take the partial derivatives to all those variables. So first the x variable, differentiate to r, differentiate to phi, differentiate to theta, and then the second one, differentiate to r, differentiate to the phi, differentiate to theta, and the third one, differentiate to r, differentiate to phi, and differentiate to theta. And then here, that is the determinant. And if you use it in your integrals, you have to take the absolute value of the determinant. So that is the absolute value. And that you see in Adams in those integrals. In those integrals, you see some vertical lines around the Jacobian. Now, if you do that, yeah, what do you get? And then I mean with the Jacobian, now if you get cosine phi sine theta minus r times the sine of phi times the sine of theta, and you have r times the cosine phi cosine theta. Now, and so you can do all those other things. And just calculate all those partial derivatives dy y. Yes, I think I have the same. Yes, and then you have to the last column you have to differentiate everything to theta. Um, yes. What do we have? Oh yeah, and then if you differentiate it to the phi, that was to the r, you have the cosine of theta. Then you differentiate to the phi, you get 0, and then you differentiate to the theta, and you get minus r times the sine of theta. Now, if you do so, you can you can calculate the determinant by, for instance, taking some column or taking some row, and maybe the I would not say that that first row is the easiest way to do. So I should do something myself. I should do something else. I should I think that I should take the last column if I want to calculate that by calculating the Jacobian. Yes, so I should take that column here. Then I know that if you have a determinants, you have always all kind of plus and minus signs. It always begins with a plus. You don't see them, but they are staying there. You have to use them later on. And so what do I get here? If I start with the last column, I see some red plus. I see some positive 1. So I get cosine theta times, and then I'm the last column I let away, the first row I let away, and I calculate the determinant of that 2 by 2 determinant, which is staying here without the plus, just the 2 by 2 determinant. And what do I get out of it? I get out of it minus r squared sine squared phi times sine theta times cosine theta, and then you have to subtract the other thing. You have this one times that one minus this one here, and we have minus r squared cosine squared theta, and you see also a sine theta cosine theta. Now that is the first thing. Then I go to the second one. In my column I see a 0. No problem. And I have then the last one, and the last one, what do I get? I see a plus, a red plus, so I have not to change something, so I get minus r times the sine of theta, and then I have some other 2 by 2 matrix, and that will be the 2 by 2 matrix, which is staying there above, and there I have to take the determinant of it. And so what do I get? I get r times cosine squared phi times the sine squared theta, and minus, and then be careful, you have here a minus r in the front of it, so you get plus r sine squared phi sine squared theta. Now, here I have my Jacobian, and now I try to add all those things. I see, for instance, here I see cosine squared, and now if you add them together, you get +1. And I see here also a cosine squared and a sine squared. So what do I get? I get minus r squared, and then I have times cosine squared theta times the sine of theta, and I have minus, I hope that you see that you have also r squared, and that we have sine squared times the sine of theta. Now, and if we add this together, what do we see? You have the cosine squared theta, sine squared theta, you can add together, and we have minus r times the sine of theta. So the Jacobian is this one here, and so we have the correction term that will be the absolute value of that Jacobian, and then dr, d phi, d theta. So with the spherical coordinates, we have to take the absolute value of that value we have just calculated. We have to take of this one here the absolute value, and we get out of it r times sine theta dr d phi d theta. And look, the phi is greater or equal to 0 and less than pi, and that means that the sine of theta is also positive. And if you take some other coordinate transformation for your sphere, maybe you will get some other correction term, and be careful. So for those spherical coordinates, and I have and now I see I have forgotten here something. You have an r squared, yeah, r squared. So this is your correction term. So you have your dv, and if you do the same as we have done with 2 in the r2, that was dx dy, down here dx dy dz, and then we have here that becomes r squared times the sine of theta dr d phi d theta. So keep in mind, important. Um, and yeah, what can I tell more about it? free by free determinant. It gives you some parallelepipedum of yeah, parallelepipedum, and now in this case we calculate in certain sense the volume of a parallelepipedum of those three vectors which are staying there in the matrix. Now, and I think that I let it with this here for this part.